No,
everything's too deep. If you think about it too deep, but yeah. We're going back to
Fine. I'm glad you have a question.
It's the next one.
We're gonna do that in class. But you can still ask me.
So I got this, but then I was looking at it and it has this next to the T. Is it because it's K over 1? Or does it have to be?
So let's just see. You have this. So you brought 2pi over, and you squared both sides. And then you brought the K over. And you're saying the answer key is something different?
It just has the K times the T.
Ah, yeah. So what they did was they went ahead and squared the top and the bottom. So you have to square the T, that's T squared. Square the 2, that's 4. Square the pi, that's pi squared.
Okay.
That way you just have K T squared over 4 pi squared.
Okay.
Yeah, try that out. Square the top and the bottom. Does it do the right time? This is all. Yes.
Never said that.
Let's see how this is what do we get?
Oh, sorry.
What's that?
Oh, it's like a button situation. Sorry.
All right, folks, let's proceed. Is everyone back? Come on back, folks. So, we're going to do a similar problem, which I hope you all find to be good practice.
like I said, this one will be on the test, or something like it. And there's a lot of parts to it. So let's take it one step at a time and see how all these parts work together. So we have an equation here, and I'll go ahead and show it to us. It is the square root of x plus 7, and then that's plus 5 minus x. So there's our graph. Sure enough, it just has one x-intercept, and the x-intercept appears to be 9. So there we have it. We know that 9 is our solution. So now let's do the algebra and see how to get there. So we'll go and write down root x plus 7 plus 5 equals x. Folks, notice how important this little tail end of the square root symbol is. What should I do to my really long square root symbol here? Because I don't want to cause confusion that it actually goes over the 5. Right? Because that would change the whole thing. I really want to be careful and shorten that up and make sure the square root line only goes over the 7. And nobody would think that it's going all the way over the 5, because that would change the whole equation. Okay, so what do I do first? Yeah, we need to isolate the root. That's our first step, is isolate the root. So we'll go ahead and move the 5 over. So now we have isolated our root of root x plus 7 equals x minus 5. That was the first step of the strategy, isolate the root. Now that we have isolated the root, we can square both sides. So we'll square both sides. I suppose we could start writing this down. So like first we isolate the root, then we square both sides. There's some good steps to write down. In terms of squaring the root, that simply cancels. So we have x plus 7. And then you want to try the double it, square it rule. You start by writing down x squared. So what's negative 5 doubled? Negative 10. And what's negative 5 squared? Positive 25. So in terms of showing work, I know I say a lot about show your work, show more work. But that's perfectly fine. If you can do the double it, square it rule, you can just write it down. If you do want to go somewhere else and show how to FOIL that, you can do that too. Okay, so we did that. Now what? Yeah, we want to move everything to one side. We want to get it into standard form. So we put everything into standard form, which means the whole equation equals 0. So I'll go ahead and subtract an x from both sides. I'll subtract a 7 from both sides. That way those both cancel out. And I have x squared minus 11x plus 18. And all of that equals 0. So in terms of our steps, we isolated the root, we squared both sides, and now we're putting it in a standard form so that the whole thing equals 0. Now what? We do what? Yeah, we have to factor. So we ask ourselves the question, what do you multiply to get 18 that you add to get negative 11? And I will show a little bit of work for that. I'm going to do my factor table. So we got 18, that's 1 times 18, or 2 times 9, or 3 times 6. So which one of those, if I multiply to get a positive number, that means I'm multiplying plus times plus or minus times minus. I need them to add to negative 11. So which numbers? Yeah, negative 2 and negative 9. So now I have factored. That's x minus 2 times x minus 9. And so now we can do the 0 product rule. Where we can say that if you have something times something equals 0, then one of them has to equal 0. So we say either x minus 2 equals 0 or x minus 9 equals 0. So solving both of those, we get x equals 2, and we get x equals 9. So we already knew our answer ahead of time. What was our x-intercept? Our x-intercept is 9. So the original equation only has one solution, and that one solution is 9. But you see, we transformed that equation into a quadratic, and a quadratic has 2 solutions. because it's a parabola that dips down below the x-axis twice. So now we have two solutions for the parabola, but only one of those solutions still works for the original. So how do we check? Yeah, we have to write down the original equation twice. So root x plus 7 equals x minus 5. Oh, now should I write down the original equation, or can I write down this?
Either way.
Yeah, either way is fine. If you write down the original, or if you write down what we transformed it into, but what you can't do is write down the quadratic. Because if you wrote down the quadratic, obviously both of those solutions would work. It has to be the original equation. So maybe we should just be hardcore about this and write down the original equation. That's the best proof you can possibly give as to whether or not something makes the original equation true, is writing down the original equation. So we'll try 2 first. Let's try 2. If we plug in 2, 2 plus 7, plus 5 equals 2. Now, by the way, folks, before we do anything else, we can already tell this is false. Here's something plus 5 equaling 2. Now look at this thing. It's a square root and it has to be positive. Can a positive number plus 5 possibly equal 2? No. So this is already no good. Well, let's just go ahead and finish the problem anyway. That's root 9 plus 5 equals 2. And see, the square root of 9 is plus or minus 3. But in this context in the equation, it's only plus 3. And so we have plus 3 plus 5 equals 2, which is 8 equals 2, which is false. So we come back here to x equals 2, and we write extraneous. Right. Well, that was just checking one of the solutions. Now we check the other solution. Boy, I should probably give you like not just half a page, but maybe like 3/4 of a page to do this one. What do you think on the test? Give you a lot of space. Oh, really? Just half a page is fine? Okay. All right, well, let's plug in the other one now. So the original equation, root x plus 7 plus 5 equals x. Now we plug in 9. 9 plus 7 plus 5 equals 9. Now again, see, we can already tell that this could be true because something plus 5 could equal 9. A positive quantity plus 5 could equal 9, especially if that positive quantity is 4. And so let's find out. That's root 16 plus 5 equals 9. And the square root of 16 in this case is just 4. And so 4 plus 5 equals 9, which is 9 equals 9, which is true. So x equals 9 is the only real solution.
So we wouldn't find the square root of 4. We just stop it.
Correct. That's absolutely right. And John, thank you so much for bringing that up. I've seen that so many times in my life where you give someone a square root to do, let's say especially the square root of 16. And so they'll do the square root, and then they'll see 4, and then they'll think, hey, 4 is square rootable, and then they'll do it again. But see, nobody told us to square root the 4. They just said to square root the 16. That happens a lot. So like, what would be another one? Like the square root of 64. I've seen people do this. They want to do the square. Oh no, that one doesn't work. I guess 16 is the perfect example. Oh no, 81. Here's another one. So you want to do the square root of 81, and you get the answer is 9, and you're like, hey, 9 is square rootable, and then you just keep going. But again, you just stop. Yeah, thank you, John. That's a great point. I've seen that mistake a lot. All right, folks. Well, that's the end of the problem. So everybody has it written down? Okay. So we have just a couple problems left. There's nothing to graph for these next couple of problems. They did give us an equation, but the equation, we're not actually trying to solve for a solution. They're just asking us to solve for a particular variable. Let's see here. So it says solve the formula for the indicated variable. What is that? T equals 2 pi L over K. What is that formula? What's that? Right, yeah, they want us to solve for L. But my question for you is, what is that formula? You know, like it'd be one thing if the formula said E equals mc squared, or A equals pi r squared,
Geometry.
or you know, A equals 1/2 base times height. Like there's a lot of formulas that we recognize. Do we recognize this formula at all? From what?
Pi, just the pi.
The pi part looks familiar. What do you think that this represents? Take some wild guesses. What do you think T represents? Time is a really good guess. It could represent time. What do you think L represents?
Length.
Probably a length. A length of what?
Distance.
Well, T is already time, and length is a distance. What do you think we could be talking about right here?
Dropping something?
A what?
Dropping something?
Good guess. Maybe we're talking about dropping something. This could be the formula for how long it takes time something to drop if you drop it from a certain height L. Right? Really good guess, Oscar. It's incorrect, but really good guess. Anyone else have a guess as to what this could be talking about?
Distance traveled.
A what?
Distance traveled.
I can't hear you.
Distance traveled.
Distance traveled?
Yeah. No.
I mean, there is, L is there for some sort of a distance travel. That's true. Well, I'd like to show it to you, folks. Let's see.
Speed.
I didn't look for this ahead of time, so I'm not sure if I'll be able to find one. Oh, there we go. This is what they're talking about. What is this?
Oh, spring. Say the spring.
It's a spring. Yeah, it might not be a very good, you know, it's just a computer simulation of one, but it's a single spring. So it's a little spring, and let's see, I can grab it and everything. So you can grab the spring and set it in motion. And you'll notice that over time, it is slowing down. Can you tell that it's slowing down?
Yeah.
And eventually it's going to slow down and it's going to stop, just like a real spring in real life. So let's go back to this formula here. T equals 2 pi, the square root of L over K. Okay, stop. There we go. Trying to find the middle point. There we go. So folks, what this formula states is, how long does it take time for the spring to oscillate once? Okay, so I'm going to grab the spring, I'm going to stretch it out, and how long will it take for it to go once? That long. Okay, so did you see how long it took? So starting right now until then. So that's the time that we're calculating. The time for a spring to oscillate once. What do you suppose influences how long it takes the spring to oscillate once? Yeah, the length of the spring, you know? Like, depending on how far I drag it. If I just drag it a little bit, then that's how long it takes for it to oscillate once. Whereas if I drag it a lot, then that's how long it takes to oscillate once. So that's one thing, is the length of not just the length of the spring, but the length of how far you drag it away from the center point. Yeah, absolutely. So then what do you suppose K represents? It's on the screen here if you can see it. You've got the mass of the bob. You've also got the dampening effect. The dampening is how quickly the spring slows down. So look, I just changed it to 0.8. Oh, geez. It slowed down awfully quick that time, didn't it? So that spring is very dampened. Whereas you could take away all dampening effects, and then the spring would just keep going forever. Wouldn't that be nice? Just forever and ever. Would you put this up in your room? No, like a real thing. Like if you could take a real spring and then have it bounce up and down in your room all day long, wouldn't that be hypnotic and fun? It'd be a nice piece. You could put it in your living room, you know, maybe in your bathroom. I don't know. It'd be kind of fun to look at. Okay, so what's the other thing that we have here? Spring stiffness. So I'm not sure how that's going to show here, but here's a spring stiffness of 1. And, okay, that's a spring stiffness of 1. Whereas what if I make the spring a lot more stiff, like a 10? Oh, did you see what happened? Let me change this to 100. Do you see? I just made, whoa, there. The spring stiffness is a lot stiffer now. I changed it to 100. And so it's a really hard spring. Whereas if I go back to a spring stiffness of just 1, you know, it's a really loose spring. Okay? Well, anyway, this is fun, and that's what the formula represents. Let's go back and look at the formula, and I'd like you all to label it. The L is the distance dragged from center. Okay, so that's how far you drag the spring before letting it go. And then the t is the time for one oscillation. The 2 pi is a constant. So 2 pi is 2 times 3.14, which is 6.28, which is technically the circumference of a circle. If you recall the formula for the circumference of a circle, the circumference of a circle is 2 pi r. So if you have a circle whose radius is 1, the circumference of that circle is just 2 pi, which is 6.28. So isn't that interesting? That somehow the time it takes for a spring to oscillate back and forth is related to the circumference of a circle. That's pretty wild right there. All right, and then finally, what does the K represent? The K is actually spring stiffness. Now, you might say, Mr. G, I saw something else on here called the mass of the bob. This is fascinating. So hold on. I liked that. I liked a stiffer spring. That was kind of fun. There's this. Okay, there we go. That's a nice, good oscillation there. Does it show the time? I don't even see it showing the time. Well, you can just watch. What happens if I move the mass to 0? Oops. Simulation is stuck. Oh, not a number. Oh, no. Oh, no. Oh, it's broken. Oh, I can't even go back. Oh my gosh, this is the worst. It is frozen. How do I even get out of here?
Delete.
All right. Well, let's see. That was my physics lab. Okay, it was my physics lab. Jeez. I hope I can go back and find the same one. My physics lab. It's not ending.
You have to.
Oh,
Yeah.
and now, thank you. All right, let's try that. Oh, something happened. Oh, here we go. Hey, do you think I can just go into history? Where? I don't even see
Take
history.
it back to that same page.
Well, I'll just type it in again. What did I type anyway? Spring simulator. There it is. Okay. All right, we're back. So watch what happens when I change these. Okay, I'm going to have no dampening effect, so it keeps going. I'll have a stiffness of 10, so it's pretty fun. There we go. That's nice. Now watch what happens when I change the mass, not to 0. So the mass is 0.1. Whoops. And now the mass is 10. Whoa. Oh, goodbye, spring. Okay, it's still going that way. It eventually is going to come back. At least I think it will. Oh, or not. Wow, that was too massive. How do I reset? Okay, well.
Change the mass.
I did change the mass. It's still gone. Maybe if I go back and then come back. Okay. All right. Well, anyway, maybe that's enough playtime anyway. So the key is I wanted you to see that this is a real thing. This is a real formula. In a math textbook, when they give you a formula, it represents something real, and it's interesting to note. Okay, so what is this problem want us to do anyway? They just want us to manipulate the formula and solve for L. So how do we solve for L? L is trapped underneath this square root. If we tell the story of L is being divided by K, square rooted, and multiplied by 2 pi. So what do we do first? We divide by 2 pi. And dividing by 2 pi, pretty straightforward. We can go ahead and divide both sides by 2 pi. And that gives us t over 2 pi equals the root of L over K. Okay, L is being divided by K and square rooted. So what would we do now? Notice that the strategy we've been using all day, isolate the root and then square both sides. Have we isolated the root? We can square both sides. And that cancels the root. And so now, how do you square a fraction? Let's remember. You square both. You square the top, you square the bottom. So let's write that out. The top is t squared. And now the bottom is 2 pi squared. We'll have to think about that. What is 2 pi squared?
6.286 squared.
Ah, now that's true. We could get a decimal, but let's leave it as 2 pi. How do we square 2 pi? What is 2 pi times itself? Yeah, let's write it down. 2 pi times 2 pi. That means 2 times 2 is 4, and pi times pi is pi squared. So now what we really have is t squared over 4 pi squared, and that's L over K. So how do we finish solving for L? Multiply both sides by K. Now, very interesting, believe it or not. What we just found out is, how long would I have to pull the spring? That's what we just solved for. So let's just say that you knew I want a spring that oscillates at 1 second intervals, right? Why do I want a spring that oscillates in 1 second intervals? Because then I could make a clock, or then I could make a watch. You know, wouldn't that be nice? If I could make a spring oscillate exactly 1 second per swing, I could make a clock out of that. And then I'd have a grandfather clock or a desk clock or whatever you like. So the question then is, if I know the time that I want it to oscillate, which is 1 second, then I can just calculate how long I have to pull it before I let go. So if I plug 1 in for time, 1 squared is 1 times the spring stiffness divided by 4p squared, and it will tell me how long I have to pull the spring away from center before letting it go. And then I will have created a 1 second pendulum. Okay, well, that's it. That's it. Yeah, so just a little bit of symbolic manipulation. You'll definitely have a question like that on the test where you're going to isolate the root, square both sides, and then you're able to get whatever you need. You know, whatever variable they're asking you to solve for. Question about that one? Yeah, I'll do.
It's not about this one, but you put test on Tuesday.
Yeah, this upcoming Tuesday. Yeah. All right. Next formula. What is that formula? It says R equals the square root of S over 4 pi. What's that, Zeno?
Isn't it kind of something? A little bit different.
It looks a little different. It sure does.
Is it rate and speed?
It could be a rate and a speed. Good guess. Is R the rate and S the speed? What's the difference between rate and speed? It's a good guess. It is not correct, but it was a wonderful guess. Anybody else? Any thoughts about what R and S? R for radius. That's a very good guess. That is correct. R stands for radius. Any guess about what the S stands for? What? Speed?
Yeah.
Maybe speed. I suppose that could make sense if you were swinging a lasso over your head. And the radius of the lasso of the circle that you're spinning and then the speed of the object. It's a very good guess. It is not correct.
Surface?
Surface what?
Yeah.
Surface circumference. I don't know what that means, but surface area is the thing. Yeah, surface area of a what? Surface area of a sphere. The surface area of a sphere, let me see if I can get a nice app here to show us this. There we go. Isn't that nice? Here's a sphere. There you go. Can you tell it's a sphere? It's a three-dimensional sphere. And we're calculating the surface area of that sphere. Why would you need to calculate the surface area of a sphere?
Maybe globe.
To make a globe. Yeah, like let's say you wanted to make a globe, you know, for someone to look at the earth, so you can spin it and have fun and all that. So that would give you a cost estimate of how much it would cost you to make the globe, and then you'd know how much you'd have to sell the globe for, depending on what materials you used. What's another sphere you make besides globes?
Basketballs.
Yeah, there you go. Maybe you guys have heard of sports. Sports is this thing where people run around and do things with different items, and like one is a basketball. So that you can calculate the surface area of how much rubber or whatever you'd need to build said ball. Yeah, so surface area is important because it'll give you an idea of how much things cost. So what is the surface area of a sphere? Let's write down that formula. S equals 4 pi r squared. That's the surface area of a sphere. So let's denote that. That's the surface area of a sphere. And the only thing that a sphere has, really, is a radius. So is that the formula they gave us?
Yeah.
Not really. What formula did they give us?
Over radius.
They gave us the radius equaling the square root of s over 4 pi. Now, rather hilariously, what do they want us to solve for? S. And what did I just tell us?
Yeah, so
Yeah, I just did tell you the answer. But I mean, because that's the standard way of saying the surface area of a sphere. That's how it's written. So anyway, I just wanted you to know what we're even talking about. So let's take the equation they gave us, which is r equals the big square root of s over 4 pi. And let's practice the actual skill that we need, which is how do we manipulate this equation to get our s back? So looking again at s, the story of s is being divided by 4 pi and square rooted. So what would we do first? We would square both sides, which again, the strategy of this day tells us that if you isolate the root, you square both sides. So the root is already isolated, we square both sides, and that cancels the root on that side. So now we have r squared equals s over 4 pi. Yep, and then you multiply both sides by 4 pi. Because s is being divided by 4 pi, you can multiply by the 4 pi. And that gives you s equals 4 pi r squared, which is the formula we expected, 4 pi r squared. I would like to point out to you that this is actually really interesting. This is a really interesting formula, the fact that it's 4 pi r squared. So watch this real quick if I can do a good drawing here. Here's a sphere, and by that I mean like the globe, like the Earth. Let's just say that it is the Earth. How did I do? That's the equator going around the equator, and that's the Earth. So take a look at the circle, which is the equator. Okay, see that circle? That circle, which is passing through the middle of the Earth, passing through the magma and the lava and going all the way to the center of the Earth. That circle right there, what's the area of that circle? The radius of the Earth is r. What's the area of just one circle? It's just pi r squared. The area of a circle is pi r squared. Whoops, not 4 pi r squared, silly me. It's just pi r squared. That's the traditional classic formula for the area of a circle. So here's what I want you to imagine, okay? Take the entire Earth, all right? And imagine the circle that's cutting through the center of the Earth, okay? All the way through the center of the Earth, all that lava and magma, it's going all the way through the center. Or you could imagine like taking an orange and cutting it in half. Take the Earth, cut it in half, and just open it up and look at it, okay? There's this circle that is the center of the Earth. Okay, how many, now, take that circle that's running through the center of the Earth, turn it into a blanket. All right, so I've got this nice big blanket, and it looks like that. Okay, so I've got a blanket that's the size of the entire middle portion of the Earth. How many blankets would I need to drape over planet Earth to keep it warm at night? How many such blankets would I need to exactly cover the entire surface of the whole planet? 4. Because the formula is 4 pi r squared. So isn't that interesting? Yes, yes, yes. Whoa, so interesting. Yes, it's interesting that if you wanted to make blankets to cover the Earth, you would take a blanket the size of the equatorial circle. You'd make a blanket that big, and then you would need exactly 4 of them. And it would exactly cover every square inch of the planet to keep it warm at night. Isn't that wild? Why is the answer 4? Isn't that weird? The answer is 4. I mean, why isn't it 3 or 5 or 6.8? You know, why did it come out so clean? It came out to such a nice, clean answer. 4, right? It could have been anything. It could have been a weird decimal. It could have been a square root. But no, it was 4.
Because of a perfect circle.
Because it is a perfect circle and it is a perfect square sphere, yeah. Okay, so there we go, folks. 2 more questions. Oh, good, and they're both kind of related to what we've done in the past. So number 88, the distance d in miles that can be seen on the surface of the ocean is given by d equals 1.6 root h. Didn't we already do a problem like this? How far you can see from a plane?
Yeah.
Okay, so now this one's different. How is it different? Where are we?
We are,
Ocean.
yeah.
Yeah, we're standing on the ocean. That's me in terror because I'm standing in the middle of the ocean. All right, so maybe I'm wearing some sort of special flotation shoes so that I'm standing in the middle of the ocean, which I think is terrifying because any moment a shark could come get me. So there we are, and it says the distance d in miles that can be seen on the surface of the ocean. So this is again scary. So I'm out there in the middle of the ocean. You're not near land. Okay, there's no land in sight. There's no islands, no Gilligan's Island, no Lost Island, just nothing. So how far can you see? What do you think? What is the size of your visual prison if you're stranded in the middle of the ocean in a lifeboat? How far can you see in every direction? How far do you think you can see? Let's take some guesses. How far do you think you can see?
20 kilometers.
How many? Sino says 20 miles. Anyone else? 100 miles? 5 miles? I mean, it's a good question, folks. How far can you see if you're stranded on the ocean?
180 miles.
What is that?
180.
18 miles?
180.
180.
Oh, 180 miles. Okay, wow. Yeah, so maybe a lot, maybe a little. This really is, it matters because if you're stranded on the ocean and you're like looking for a boat, right? You're all optimistic. You're like, gee, I hope I see a boat. Well, like the ocean's a pretty big place. And if on the big vastness of the ocean, you can only see around you like a little teeny bit, what are the odds that you're going to see a boat? You're like none. It's terrifying. Okay, so let's calculate it. It says the distance d in miles that can be seen on the surface of the ocean is given by d equals 1.6 root h, where h is the height in feet above the surface. So let's detail this. What does d represent again?
Distance.
Distance what?
From ocean to the.
Right, distance seen in miles. So that's how far you can see. And what does h represent? The height what? Yeah, I'm just going to say height, feet above surface. Now, first of all, that's just feet above the surface. So imagine even more terrifying, you're swimming. You have no lifeboat. Where's your head? Like if this is the surface of the ocean right here, where's my head? Barely above the surface? How many feet above the surface am I? Like 1? So like if you're stranded in the ocean and you're swimming, you're only really 1 foot. I mean, maybe if you tried really hard, you could like temporarily wiggle yourself up out of the water like a foot or 2. So how far can you see if you're stranded in the ocean? Let's do it for the 1 foot case, first of all. How far can you see if you're stranded and your head is just 1 foot above? So that'd be 1.6 times the square root of 1. So how far can you see? 1.6 miles. That's it. So from your little head bobbing above the water, you can see 1.6 miles in all directions. And that's it. What is the question actually asking us? How high would a platform have to be able to see 20.5 miles? Right? 20 miles, that's even better. Like that increases your chance of seeing a boat and a boat seeing you. So how high would the platform have to be? Where do we plug in the 20.5? Yeah, we want to be able to see 20.5 miles. So we have to put the 20.5 here and then solve for h. Right? Because we want to be able to see 20.5 miles. So how high above the surface would we have to be? So how do we solve for h? H is a root. So what do we want to do with that root? Isolate it. So we're going to divide off the 1.6. And whatever that is. So 20.5 divided by 1.6, that gives me 12.8125. That's equal to the square root of h. So now that we isolated the root, we can square it, And that gives us 164 feet. 164.16 feet. That's pretty tall. How tall of a building is that? 164 feet. How many feet is one floor? I mean, I'm 6 foot tall, so how tall is the ceiling? Maybe 10, maybe 12? Let's say that one floor of a building is 15 feet if you account for the fact that there's ceiling and ductwork and stuff. How many times does 15 go into 164? Just over 10. It's about an 11-story building. That's an 11-story building. So what are the odds of you having an 11-story building in the middle of the ocean?
Pretty good.
Yeah, pretty good. Exactly right. Pretty good. All right. So again, folks, this is a real formula. You know, it's not just something they made up. It's a real formula. Okay, the last one. I know I just have a second here, but let's just take a look at it. It says the time t in seconds for a pendulum of length L to make one swing. So that's a pendulum, not a spring, but it works the same way. It's given by t equals 2 pi root L over 38. I haven't forgotten. I want to give you your quizzes back too, but let me just write this down. So this formula is t equals 2 pi root L over g, where g actually represents the gravity of the planet you're on. So this formula is talking about Earth. So it's t equals 2 pi root L over 38, which is a representation of the gravitational force on Earth. So they're just saying, how long of a pendulum would you need to make a swing in 1.4 seconds? So where do I put the 1.4? In for t. So I'd have my 1.4 equals 2 pi root L over 38. And your job, they're saying, how long would the string have to be? So what do you have to do?
Isolate the L.
Yeah, you have to isolate L. You have to get L by itself. So you would go ahead and divide off the 2 pi. And this now you can actually go ahead and do in your calculator and get a decimal. You would do 1.4 divided by 2 pi. Make sure you use parentheses for the 2 pi. And then that would be 0.2228 equals root L over 38. And now that the root is isolated, you can square both sides. And since that number is still in my calculator, I can just hit square. So now that's 0.0496 equals L over 38. And since L is being divided by 38, I multiply by 38 on both sides. And that number is still in my calculator, so I can just hit times 38. And I got a length of 1.88. Sorry, I know I did that kind of fast, but I know that class is almost over, and I bet you guys would like the quiz back so you can get going. So here's...
You got 8.
Hold on 1 second. I think I have some. Let's see. I did. Casino. Oh, Jackie, I have some more for you. Oscar, Jennifer.
Can I
Oh,
get
Jackie, I have more for you. Oh, that's right. You weren't there.
I can fix the grade right.
What?
I can fix the grade right.
Well, did you ever send me that extra credit email?
Yeah.
That was worth 10 points.
Oh,
So that more than makes up for it. You know, I don't think I have it right now with me, but if you just come with me to my office, I'll give you one.
Okay.
Let me just look. I don't think I do.
Okay.
I do not. But if you come up to my office, I have plenty.